Dear students, in the last class, we discussed about construction and working of carbon dioxide laser. In the today's lecture, we are going to discuss semiconductor laser construction and working. Before going to construction and working, let us have a look on the phenomena involved in the emission of radiation in case of a semiconductor laser. We know in a semiconductor, there is a valency band and conduction band. Both are separated by a small energy gap. And conduction band is having free electrons which are taking part in the current conduction, and valency band is having weakened energy states. Those are named as a valency band. Both are separated with small energy gap. If in a semiconductor there is a excess number of electrons in conduction band and excess number of holes in valency band, excess number means if the system not in equilibrium, then we will have this excess number of electrons and holes. These excess number of electrons and holes are not stable. That's why they will come back from the conduction band to valency band, combine with the hole, and one electron hole pair is annihilated. This phenomenon of annihilation of electron hole pair is known as recombination. In this recombination process, the energy is emitted. If the energy is emitted in form of radiation, that kind of recombination is called radiative recombination. So the radiative recombination process is the responsible to give the emission of radiation in case of semiconductor laser. If in a semiconductor, if there is a presence of excess electrons and excess holes, because of their short lifetime, these excess electrons are come back to the conduction band to valence band and combine with the hole, and emission of radiation takes place. This kind of recombination is called radiative recombination. So, if you observe this phenomena, what you understood here, to get the emission of radiation, what is the necessary condition in this case? We need more number of electrons in conduction band and more number of holes in valency band. Then only the continuation emission of radiation process takes place. That situation is called population inversion. So in case of semiconductor laser, what is the population inversion? More number of electrons in conduction band and more number of holes in valency band. But if you take an N-type semiconductor, in case of N-type semiconductor, we are having more number of electrons. So if you take a pure semiconductor doped with pentavalent impurity atoms, the resultant semiconductor is known as N-type semiconductor. How you will get the N-type semiconductor? A pure semiconductor doped with pentavalent impurity atoms, the resultant semiconductor is called N-type semiconductor. In that we will have the more number of electrons, not holes. Or suppose if you take a pure semiconductor doped with pentavalent impurity atoms, those will occupy energy level nearer to the conduction band. If you give small amount of energy, they donate the electron to the conduction band and become electrically positive. So they donate the electron to the conduction band. That's why these atoms are called donor atoms. This energy level is called donor energy level. So by donating the electron to the conduction band, they become electrically positive. These positive ions are immobile. They are not moving. They are not taking part in the current condition. These electrons only taking part in current condition. So in case of semiconductors, there are two kinds of charges, mobile charges and immobile charges. Mobile charges are moving, take part in current condition, and immobile charges are not moving, they are creating the space charge. So these are immobile charges, these are mobile charges. So in case of N-type semiconductor, we are having more number of electrons, but we don't have more number of holes. We will have some number due to intrinsic excitation, but the number is very, very less. So if you take a P-type semiconductor, in that we are doping the metal with trivalent impurity atoms. Those will occupy the energy level nearer to the valency band. They accept the electron from the valency band and create the holes here. So that's why these atoms are called acceptor atoms and this level is called acceptor level. In case of P-type semiconductor, we are having more number of holes, but not electrons. So if you get the emission of radiation in case of semiconductor laser, we need more number of electrons in conduction band and more number of holes in valence band. That is possible only with PN junction. If you take a PN junction, here having taking a N-type semiconductor and a P-type semiconductor and form a junction here. So in N-type semiconductor, we are having more number of electrons, and in P-type semiconductor we are having more number of holes. And corresponding to this every electron, we are having immobile ionized donor atoms. Corresponding to every hole in P-type, we are having immobile ionizer acceptor ion. So these are immobile charges. These are only mobile charges. If you form a PN junction, we are having more number of electrons here. So here very less number of electrons. That's why these electrons are start diffuse from the high constant area to low constant area. This phenomenon is called diffusion. So if you these excess electrons comes here and combine with the hole, then what happens? One electron hole disappears here. These excess electrons comes here and combine with the hole, and electron hole disappears. This phenomenon is called recombination. In this recombination process, the energy is emptied in form of radiation. That kind of recombination is called radiative recombination. Okay, if system is in equilibrium, that means we are not applying any biasing. Then what happens now? These immobile charges, they are creating the space charge here. These negative ions are opposite the further diffusion of electrons, and these positive holes are opposite the further diffusion of holes here. That's what happens here. There is no further recombination. We don't get any radiation here. But if you apply some external bias here, forward bias, if you apply some external forward bias, then electrons are injected here and holes are injected here. Then recombination takes place in this region. That region is called active region or depletion region. So if you want to get the emission of radiation continuously, we have to apply the forward bias. When you apply the forward bias, then these electrons are injected here, these holes are injected here, they are recombined. Due to the recombination, emission of radiation takes place here. That's why semiconductor laser not possible only with N-type, not possible with only P-type. It is a combination of N and P. So semiconductor laser is a PN junction. But we need more number of excess carriers here. So that's why we have to dope heavily. So semiconductor laser is a heavily doped PN junction. If it is heavily doped PN junction also, electrons and holes are not available in the depletion region because system is in equilibrium. So we have to apply some external bias. When you are applying external forward bias, these excess carriers are injected here. They recombine and gives the radiation. That's why finally we can tell semiconductor laser is a heavily doped, properly forward biased PN junction. So what is semiconductor laser? Semiconductor laser is a properly forward biased, heavily doped PN junction. What is the necessary of heavily doping? To get the more number of electrons in conduction band and holes in valency band. What is the meaning of more number of electrons and holes, electrons in conduction band and holes in valency band? That is nothing but population inversion. So how we can achieve the population inversion in case of semiconductor laser? We can achieve the population inversion in case of semiconductor laser by heavily doping. What is the necessary for forward bias here? To inject the carriers in the active region for recombination, a minimum current always made to flow across the junction. That minimum current is called threshold current. So to initiate the latching action, always a minimum current made to flow across the junction. That minimum current is called threshold current. That can be achieved by this forward bias. That's why semiconductor laser is a properly forward biased, heavily doped PN junction. Heavily doped PN junction provides the population inversion. What is the meaning of population inversion? More number of electrons in conduction band and holes in valency band. What is the necessary of forward bias? So that can provide the a minimum current made to flow across the junction. That minimum current is called threshold current. Once the current flow across the junction is more than threshold current, lasing action will be initiated and we will get the laser beam. Okay, so what is the phenomena here? I already explained. We have to inject the excess carriers by applying the external field, and they can recombine radiately and gives the radiation. So this phenomenon is called injection electroluminescence. What is the phenomena gives the emission of radiation semiconductor laser? Injection electroluminescence. What will happen here? When you are applying the forward bias across the heavily doped PN junction, these excess carriers are injected into the active region by means of external field and recombine radiately and gives the radiation. What is the material we are using mostly? Mostly we are using direct band gap semiconductor. In this direct band gap semiconductor, the electrons are directly moving from the valency band to conduction band. Sorry, the electrons are directly moving from the conduction band to valency band and recombine. That kind of recombinations are called direct recombination. What kind of material we are mostly are using? Direct band gap semiconductor. What will happen in case of direct band gap semiconductors? Direct recombinations are taking place. What is the direct recombination? The electrons are directly moving from the conduction band to valency band and recombine. And the primary choice for direct recombination is radiative. So that's why mostly we are using direct band gap semiconductor, because in the direct recombinations are taking place, direct recombination primary choice is radiative. Examples are gallium arsenide, gallium phosphide, indium gallium arsenide, indium gallium phosphide. Okay, and now construction here. So construction is, we are taking a PN junction here. This is the gallium arsenide N type, and this is the gallium arsenide P type. A junction is formed. In that, this is the depletion region. That is nothing but active region. In that, recombination is taking place and the emission of radiation takes place. And top side, we are connecting a metal contact here. And below that also we are having metal contact. Further, we are connecting leads here. Further, we are applying the forward bias here. This negative is connected to N type and this positive connected to P type. Okay, it's a N type, P type, active region where the recombination is taking place. Here metal contact. Further, we are connecting a lead, and here also another metal contact will be there bottom side. And further also we are connecting a lead, and further we are applying the biasing here, forward bias. Okay, and these two faces are covered with metal contact, and we will make the this face and the back side of this face are both are roughed, and remaining two surface, these two will make well polished, and one side we are giving the fully reflection coating, that is back side we are giving the fully reflection coating, and front side we are giving the partially reflection coating. Then the lasing action will be initiated when you are applying the forward bias, and laser beam will come from here. Naturally, the construction of the semiconductor laser we can do in three different structures. One is homostructure, other one is heterostructure, and other one is double heterostructure. Homogeneous means both N-type, P-type, and in active region also same kind of semiconductor material. Here also gallium arsenide, gallium arsenide, gallium arsenide, N-type, P-type, and active region. In all three regions, if we are having same kind of material, that kind of structure is called homogeneous structure. And here, one side we are having gallium arsenide. First of all, if we take here gallium aluminum arsenide, here gallium aluminum arsenide, but center gallium arsenide. On either side of the act region, we are having different kind of materials. That kind of structure is called double heterostructure. One side is different, but other side is same. Then we can use heterostructure. The advantage with the double heterostructure is we can confine the carriers and photons into the active region. So that's why efficiency of the laser can be improved. That's the advantage with the using of a heterostructure. What is the heterostructure? On either side of the active region, same kind of different kind of material, then we can say that is a double hetero. One side is different, other side is same as the active region, then we can say heterostructure. And all three are same, then we can say homogenation. What is the advantage of the double hetero here? The uh, excess carriers and photons are confined into the active region. They will not move here or here. That's why they remains here. They recombine and gives the radiation. That's why efficiency of the laser can be improved. And working here. So if you form a PN junction here, this is the N type. This is the conduction band and this is the valency band. And this is the Fermi energy level N side. It is a P type. Here conduction band and valency band. Here we are having Fermi energy level here. This is the P type Fermi energy. When there is no bias, the Fermi level on both sides are the same line here. Fermi level in N side and Fermi level in P side both are on the same line. So there is no excess electrons here or excess holes here. That's why there is no chance of recombination here. When you are applying the forward bias, this Fermi level start moving like this. Because of field effect, this Fermi level. So this EFN, this Fermi level moves like this. And this EFE moves down. So this EFE, this is the EFE, this one moves down. That's what happens here in the active region. Here we are having more number of electrons. Here we are having more number of holes. So then they will recombine and gives the radiation. This is the working of a semiconductor laser. So this is the situation of energy level diagram without bias and this situation of energy level diagram with the bias. In examination point of view, while we are explaining the construction working of semiconductor laser, you have to draw this diagram very neatly, very important energy level diagram. This is the working here. Without biasing, there are no excess electrons or excess holes here. So here we don't have the electrons, here we don't have the holes. That's why there are no recombination. But here when you are applying the forward bias, here the electrons are injected here and holes are injected here. So because of this forward bias, then what happens? The recombination starts and emission of radiation takes place. Now, applications of laser. So the highly monochromatic characteristic of laser is making it used in the isotope separation. We already discussed it. One of the important characteristics of laser is highly monochromatic. It is having only one wavelength here. So here, while we are exciting in a system, the atoms are excited when the energy we are giving in form of light. So if you take a isotope means they are having same atomic number, but different mass number. That's what happens. Their energy levels are different. So if you give the energy in form of laser light, there will only one kind of isotopes are excited because different energy levels are there for different isotopes. So this wavelength of the laser is suitable for only one kind of isotopes. Those only excited so that they can be separated. That's why this process is called Silex process. SILEX. Separation of isotopes by laser excitation. That is called SI. Separation of isotopes by laser excitation. LEX. So this process is called Silex. That's one of the important applications. And the laser is used to initiate the nuclear fusion reaction. We know if the low atomic number atoms are combined together, for suppose hydrogen, two hydrogen atoms are combined together, then what will form here? Helium nuclei will form. But the mass of the helium nuclei is less than the sum of the mass of two hydrogen atoms. That means there is some mass loss is taking place. That mass loss is empty in form of energy according to Einstein mass energy relation E equal to mc square. This phenomenon is called nuclear fusion reaction. So if you want to initiate the nuclear fusion reaction, we need a high energy density or power density. That means we need large amount of power in a small area to initiate the lasing action. That is possible only with laser. That also we discussed in the starting of this topic. Laser is having very high power density when compared with the sun. So that is also used for initiation of nuclear fusion. And laser is also used to measure the electron density in plasma. And then chemistry labs are used to study the nature of chemical bonds. That means you are giving the energy at what strength the chemical bond is breaking. So that can be the bond strength. For suppose at a particular range of the laser beam, the chemical bonding is breakdown. That means that is the strength of the chemical bond that can be analyzed. And in optical communication, lasers are used as a light source. In the next topic, fiber optics, we will discuss what is the role of light source in optical fiber communication. And military laser are used for ranging applications. That means if you focus the laser and touch the any object and reflect back, the velocity of the laser beam is velocity of light. You find out the time, how much time taken by the laser beam to touch the object coming back. By knowing the time and velocity, we know that is equal to velocity of light. We can find the distance of the object. So that process is called ranging application. So lasers are used for ranging application. In computers, lasers are used to read the data and write the data on the CD-ROMs. And industry, lasers are used to drilling purpose because of its high energy density. It can be used for drilling, but we can make the holes with the diameter of our hair. Cutting purpose, welding purpose, we are using the lasers. They also used in non-destructive testing method also. And in medicine, lasers are used for controlling the hemorrhage, and severe laser is used in the treatment of liver and lungs and for elimination of moles, tumors developed in the skin tissue. Lasers are used in ophthalmology for attach a detached retina. So that can be used to attach a detached retina. So that in eye operation also we are using the laser. These are the different applications of laser. And one of the application we are discussing elaborately, that is holography. So the topic is